Let's go back to the number of tosses we need to get a head when we're tossing a coin that lands heads with chance P. I've called that random variable WH for waiting till you get a head. Now you know that that has the geometric distribution on 1, 2, 3, 4, and you also know its expectation. We derive that by the tail sum formula, and tail sum calculations are wonderful, but they have a way of feeling a little mysterious. Conditioning helps us see what is going on. So we are going to redo this calculation using conditioning now. And for that, it's a good idea to start out with a simple observation, which is in order to get a head, surely you need at least one toss. And then maybe some more. The some more is a random amount, which I'm going to call R. And so this is the additional. Now, when do you need an actual additional? It's when the first toss is a tail. Right? If the first toss is a head, then you're done at 1. So let's draw a tree diagram for R. Then, as we said, it's 0 if the first toss is a head, so that happened with probability P. And with probability Q, well, the first toss is a tail. So now what? Well, once the first toss is a tail, you're still waiting for heads. So you will need one more toss, and then you will need maybe some additional. That sounds very much like what we were writing up here. And so what you end up with is this again. But an independent copy of it. This lower branch is the case where you got a tail the first time. Now, where is that first time? That first time's already here. That gave you a tail. So now after that, you're going to need at least one more toss to get your head. And so you're going to have a 1 plus an additional, which is not numerically the same additional amount, but it has the same distribution as the additional amount that you had to start with. And so in the end, you have a random variable that I'm going to call W star that is an independent copy of your original WH. And so this is the moment right here is the moment where the game starts over. And so this gives us an equation for the expectation that we want. So let x be the expectation that we're looking for. Then we start at this line here, then the expectation, x. I don't actually need that notation. I could have just called it the expectation of WH, but x is shorter. x is 1 plus the expectation of r, and that expectation of r we'll find by conditioning. So 1 plus. Now go to the tree diagram. The additional is 0 with probability p, and with probability q, well, it's the same diagram again, and so the remaining portion is just x. That's when the game starts over, and so your equation is x is equal to 1 plus xq. Isolate x on the other side, and remember that p plus q is equal to 1, and you will end up with px equals 1 and x equals 1 over p, which you knew already.